Yay!
Here's sort of an add-on to the video we just did, which is going to let us select the velocity more precisely than we did last time. So here's the idea. Suppose we send a particle, a charged particle. I guess I didn't put the charge in there, right? This is a positively charged particle. So here we go. There's our classic green positively charged particle. Okay, so we send a positively charged particle into this pipe. What I really want is I want to know that anything that doesn't have that precise speed v does not come out the end of the pipe. I guess the better way to say it is I want everything coming out of the pipe to have that exact speed v. So if a whole bunch of stuff with different speeds goes in, let's say I don't know exactly what the v is. V is some value. I want everything coming out to have the exact same speed. Here's how this works. This is kind of a neat thing. Okay, so this is an example of crossed electric and magnetic fields. And this is used in lots of different devices. So let's suppose in this pipe, on the right-hand side of the pipe, I have positive plate and the left-hand side negative plate. So this is sort of like a capacitor. So anyway, I've got an electric field inside the pipe that's going this way, right? And then the magnetic field, suppose there's also a magnetic field inside the pipe, and the field is coming out of the page. So what that means is I can write down the electric force is going to the left on the positive charge, right? The positive charge just follows the electric field. So the electric force is going to the left. And if you do your favorite right-hand rule, what you're going to find out is that the magnetic force on that charge is going to the right. So what happens is that if I can perfectly balance those forces, right? If they have the same magnitude, I already know they're going to be going opposite directions. So if they have the same magnitude, then what happens is that the particle goes through undeflected. That's kind of what I want. So to see how this is going to work, let's write down what are the magnitudes of these forces. So if the magnitude are equal, that means what's the magnitude of the electric force? It's just Q times E. The magnitude of the magnetic force, it's QVB sine theta. But again, theta between V and B is 90 degrees, so sine of theta is 1. So this is just going to be QVB. Notice it doesn't make any difference what the charge is. That's very cool. So the condition that the charges go through undeflected is just that the speed has to equal E over B, the magnitude of E over B. What does that mean? Well, consider this, because we can choose, we can sort of tune, however you build this device, you can tune what the electric and the magnetic fields are. For example, if we want, like in our last example, we had the V as being like 10 to the 6th, a million meters per second. Suppose that's what you want. Suppose you want all the particles to come out of this thing with that exact speed. So if you want that, then what you have to do is you have to make that ratio between the electric and magnetic fields in your pipe. You have to make it 10 to the 6th. So you could choose. There's an infinite number of things you could choose, right? As long as they have that ratio, you're going to be fine. So for example, I could choose the electric field as being 1,000 volts per meter, or newtons per coulomb, whichever unit you want. And then B would be 10 to the minus 3 Tesla, right? Or 10 Gauss. So if you chose your device, if you sort of tuned your device to have E of 1,000 and B is 10 to the minus 3, then the particles that make it through undeflected are going to have a velocity of 10 to the 6th. That's very cool. Because suppose they don't. Let's see what happens. Suppose a particle goes through that's a little bit greater. Suppose you introduce a whole bunch of particles with a whole bunch of different speeds. So the particles with a speed greater than 10 to the 6th, what happens? Well, the electric field doesn't care about the speed, but the magnetic field does. So if the speed is greater, the magnetic force wins, and so then they would be bent to the right. So faster Faster than 10 to the 6th. The net force is going to be to the right because the magnetic force wins. Slower than 10 to the 6th. Then the electric force wins because the magnetic force is now smaller than the electric force. And so the net force is that way. Right? So only for that exact speed do they go through undeflected. So then if you make just a really long pipe, then you can ensure that whatever comes out the end has that exact speed. So this is something that you'll come into contact with as you go through and analyze more devices. This is something that's commonly used.